So sharding and partitioning come in very handy when we want to scale our systems. These concepts operate at a database level and it helps us improve the overall throughput and availability of the system. In this video, we take a detailed look into how a database is scaled and evolved through different stages, what sharding and partitioning is, understand the difference between them, see at which stage should we introduce this complexity, and a few advantages and disadvantages of adopting them. But before we move forward, I want to talk to you about a code-based course on system design that I have been running since March 2021. Right? If you are looking to learn system design from the first principles, this course is for you. Yeah. Because this is a cohort-based course, it will not just be me rambling a semi-optimized solution thinking it's the most amazing solution out there. Instead, it will be a collaborative environment where every single person who is part of the cohort can pitch in his or her ideas and we will evolve our system around that. Right? Every single problem statement comes with a brainstorming session where we all together brainstorm and evolve our system. That's way everyone understands the kind of trade-offs we made while making that decision. Instead of just saying, hey, we'll use a particular queue, we'll have the justification why we use only that queue, why we use that particular database, why SQL, why not NoSQL, right? How are we leveraging throughput? How are we ensuring that our system scales? That's the highlight of this course. This course is taken by more than 500 engineers to date, spanning 9 countries and 7 cohorts. Right? People from all top companies have taken this course and the outline is very intriguing. It's very exciting. So we start with week 1 we start with the core foundation of the course where we design online offline integrator, then we try to design our own medium, then we go into database where we go in depth of database locking and see few very amazing examples of database locking in action and how do we ensure that our system scales through that. Then the third week is all about going distributed where we design our load balancer. I'll walk you through the actual code of a toy load balancer and understand how TCP connections are managed and how simple it is to build load balancer. Then week 4 is all about social networks. Week 5 is all about building your own storage engines. Like we'll build that intuition on if you were to ever design your storage engine, how would you do that? Right? Then week 6 is about building high throughput systems. 7 is about building IR systems, basically information retrieval systems and ad hoc designs where we design our own message brokers like SQS where we design distributed task scheduler. And we conclude the course with week 8 where we talk about the super clever algorithms that has powered or that has made those systems possible. Right? I have also attached a video verbatim as is from my first cohort where we designed and scaled Instagram notifications. I will highly encourage you to check this video out. Right? And now back to the video. So what is sharding and partitioning? A textbook definition of sharding says that it is a method of distributing the data across multiple machines, while partitioning is all about splitting the data. But before we understand what sharding and partitioning actually is and how we see them in real world, let's talk about how a database is actually scaled, because sharding and partitioning as concept are very tightly coupled with a database. So what exactly is a database? You have an EC2 server. On that EC2 server, you install MySQL server and you start the process. So that particular process is nothing but your database. And that process exposes a port and any user who wants to talk to the database talks via that port. For example, 3306, the request comes to this port, then the port is coupled with the process, the query goes to the process, your MySQL process computes the query and sends back the result. Right? And this as a database, we represented it with this very fancy symbol. Right? But in reality, this is exactly what your database is. This MySQL server uses the local disk of this virtual server where it would persist the data durably. Right? Now what happens is when you say you have this database server and you are putting it out into the production to serve the real traffic. And let's say what you are getting is you are getting 100 writes per second, which is a pretty decent traffic and you are very happy about it. So what did you do? You started with a very small server. Small server because you didn't really have money. So you started with a small server just to save cost. Obviously, why would you want to have big server to do that when you can do it with small one? You have a bunch of API servers who talk to this database to get your things done. 100 writes per second, you are extremely happy and done. Now what happens? Someone famous tweeted about your product. And your product saw an growth. So from 100 writes per second, it went up to 200 writes per second. But when the amount of writes increased onto your database, you saw a couple of metrics dropping down. So let's say CPU utilization was always around 80-90%. Your memory utilization jumped. Your query execution time increased. So then what did you thought? Ki, hey, now that I'm getting more traffic, let me scale up my instance. This is where vertical scaling comes into the play, where you start small, but as you see more traffic, more continuous traffic or more consistent traffic, you would want to scale up your database, which means you give your database more CPU, more RAM, more disk. In actual world, when you put a database in production, what does this mean? This means that your EC2 server on which you have hosted your database, you are increasing the CPU and the memory and the disk of this server. There is no change into this MySQL process. MySQL process was running before and will continue to run after. But what you did is you added more capacity into the server on which a database process is running. So now what happened is because you scaled up, you are bearing more cost. But that's okay because you are gaining business from 100 writes per second, you are now supporting 200 writes per second because you need them. So, but then what you also saw that when the writes were increased, like obviously your system is not just doing writes, but it is also doing reads, like some use cases like fetching a profile of a user and putting something into the database and then reading some more information, complex joins and whatnot. So what did you do? You found out that earlier one database instance was more than enough to support reads as well as writes. But now you have large number of reads. Although you are supporting writes by scaling up your database, to give you a helping hand, what you also created is something called as a read replica. This read replica has this exact copy of this data over here as well. So now your API server can redirect all the read requests here to this instance, while this instance is free up to do critical reads and all the writes. So this is a classical leader follower or basically master follower architecture, right? Where all the writes go to the master, reads go to this read replica. The data across both of these nodes is exact same. And here, whenever the write happens on this master, it is propagated to this follower, right? So this is how you handled 200 writes per second by vertically scaling up your machine and added a read replica to support large number of read requests coming in. But now let's say someone really famous tweeted about your product and your product went viral. It went viral like anything. And now what happens is you were prepared to handle load of 200 writes per second, but now you're suddenly getting 1000 writes per second. Now what would happen? When you get this much of write, you need to scale up again. You said, hey, let me add more CPU, more RAM, everything what it requires, because now my product is going viral, my business will take off. So let me scale up my database once again. So then you scaled it up. Now you are supporting 1000 writes per second with read replicas and whatnot. And you are very happy that your system is working fine. But then what you find is this traffic is consistent. A lot of people are using your product. And now you are seeing a lot of traction onto your product, which now requires you to handle 1500 writes per second. Now you thought, hey, as like up until now, you scaled vertically, you added more CPU, more RAM, more disk, whatever it required to handle that load. Can you not add more to this? Then you went to the AWS console and checked, hey, this is the maximum limit. Now I can't grow beyond this. So vertical scaling has hardware limitations. You cannot go beyond that particular configuration because of physical limitation on the hardware. So because vertical scaling has limit, you are capped at 1000 writes per second, but your business is growing. Now you cannot say, no, my database is not supporting, so I won't do that, because business is business. You want to make money, and why not? So that's where what you do is you then think of growing things horizontally. So a truly scalable system is always horizontally scalable, right? So that no matter how much traffic comes in, how many users comes in, you always have a plan to scale it out. So earlier with vertical scaling, we used to scale it up. With horizontal scaling, we scale out. So then what you do, you add horizontal scaling. Now you know that this big of an instance is enough to support 1000 writes per second. But now what you have to do is you have to support 1500 writes per second. So what do? Is you split the data. You definitely know that you need one more server to handle that load. But now when you add one more server to that, but each server has limit of handling 1000 writes per second, but you want 1500. So what do? Is you add one more server into this. Say first server you handle 50% of the data, and the other 50% of data the other server handles, right? And now assuming that there is a uniform distribution of traffic across the data, which means that 50% data lies over here, so 50% request would come over here for the data which resides over here, and 50% goes over here. So now when you are getting 1500 requests per second, it is equally splitted across both these servers, each handling 750 writes per second. Your physical limit was 1000, you are at 750, so which means that this one node will now be able to very easily handle 750 writes per second, and in totality you handled 1500 writes per second, which means that you, as a coherent system or as a unified system, you are handling 1500 writes per second, where your physical limit of one node was only 1000 writes per second, right? So you are able to garner higher throughput than what a single machine could offer, which is where you would always see at massive scales, companies would go for horizontal scaling because it would help them get higher write throughput and higher read and write throughput, right? So this is a classic advantage of going into a horizontally scaled database, and this is sharding, and basically this is where the concept of sharding and partitioning comes in handy, right? So this is why we actually need both of those concepts, sharding and partitioning. Here we have actually partitioned the data across two shards, so that 50% traffic goes over here, 50% traffic goes over here, and we are able to handle higher throughput. So what we just did over here is that we added one more data node. So this data node that we add is called a shard. We added a shard to our database and we partitioned the data. So partition is all about splitting the data. So database server is sharded while the data is partitioned, right? So whenever people talk, although people talk about those two terms interchangeably, but shard is at a database level and partition is at a data level, right? So overall, we always shard a database and partition the data. This is a crude oversimplification. People use term interchangeably, and partitioning is all about splitting the data. Let me give you a simple example. Let's say I have 100 GB worth of data, right? And now what I know that my one node, due to some reason, my one node cannot handle 100 GB of data. So what do? You partition the data with any of the partitioning strategy. We will take a look at it in some future video. But let's say you split this data, 100 GB data, into 5 smaller chunks of it. 30 GB, 10 GB, 30 GB, 20 GB, 10 GB, right? And now all of these partitions has to be mutually exclusive. So data present over here should not be present over here. Data present over here should not be present over here, right? So these are mutually exclusive partitions or subsets of the data. This way, what would happen is, instead of your one node to handle 100 GB of data, a node will only handle 30 GB worth of data. So this is where you do the partitioning of the data. Now, these are partitions of the data. Now, no one's stopping you from having all of these 5 partitions into one database server. Partition is only operating on the data level. You can have all of these 4 or 5 partitions on one database server, or you may choose to have multiple database servers. That is up to you. And that is the number of shards you have. So if you have 2 shards, you can split this 5 partitions across those 2 shards. Or you can choose to have all of these 5 partitions on one shard only, right? It just gives you nice isolation on traffic. So a simple diagrammatic representation of this could be like something like this. I have this 100 GB data set split across 5 partitions, and there are 2 shards over here. So what I can have is partition A and C is going on shard 1, while partition B, D and E is on shard 2. So whenever a request comes in, we need to know where does this data lie. Is it part of partition A or partition B or partition C or partition D or partition E? And then depending on where, like which partition holds that data, you would be forwarding the request to that corresponding shard. Like let's say the request came in and you know that this data is part of partition B. So then the request would come in, you know that it is on partition B, you know that partition B lies on shard 2. So you'll forward the request to database server, which is shard 2, and within that it would hit that particular partition to get the data. Right? So partition is all about splitting your gigantic data set into smaller chunks of data so that you have to operate on that small chunk. And now if you want to ever move the partition, let's say partition A is very hot, which means a lot of requests are coming onto this, because of which partition C's performance is getting affected. So because it is a partition, you can actually physically take this and move it to your shard 2. This is called load balancing. Load balancing across partitions. So partition as a logical entity gives you that superpower of quickly moving your partitions across shards. Right? And that is the advantage of doing partitioning of the data. So shards are physical servers. Again iterating, shards are physical servers. Partitioning happens on the data part. Right? So how do we partition the data? So there is no one global rule of partitioning the data. But there are two categories of partitioning. First is horizontal partitioning. Second is vertical partitioning. So horizontal partitioning operates at document level or row level. Vertical partitioning operates at column level or table level. We will take a detailed look into partitioning strategies in some future video. But how do we partition? So like when we talk about just splitting 100 GB into 5 partitions, this logic cannot be random. There has to be a deterministic way of doing it. And it totally depends on the load you have, the use case you have, and the access pattern you have. You cannot just randomly say, hey, this partition or this is how I will partition the data. Like randomly allocating some row to some partition will have a very massive impact on your performance. It has to be a very smart way of doing it. And it totally depends on the use case you have, the access pattern you have, and the overall load you have. Right? And we will talk about partitioning in detail in some future video. But now let's take a holistic view on what partitioning and sharding together looks like. This is one diagram that I always used to explain people what partitioning and sharding is, just sharing with you what happens. So let's say when we talk about sharding and partitioning, yeses and nos. So in all 4 cases we will consider. So a database server with no sharding and no partitioning is something that you do locally. You on your local machine you spin up, or on one server you spin up one MySQL, you install one MySQL database, you create a database within that and you start using that. So that is your one EC2 server within which one MySQL process is running, within which you have your data that you are operating on. The day 0 architecture where you had one database instance and everything into this. So that is not sharded, not partitioned. Right? But when you say that you have not sharded, but you have partitioning of your data, this might be logical partitioning that you are doing, in which you are splitting your data across 2 partitions, but keeping both of them on the same shard. So your data is logically partitioned, maybe let's say multiple tables or multiple logical partitions of data that you are doing, and keeping them in one database instance only. A classic example of this is on a MySQL server, you can create 2 databases. Right? So by firing command create database, let's say you want to support 2 applications. One is let's say airline check-in system and another is let's say ticket booking system. Right? So you type in command create database airline, create database basically ticket booking system. So this creates 2 logical databases in one MySQL server. These are those 2 databases. That is partitions. Right? So when you have not sharded your database but you have partitioned it, this is how it looks. Right? And then let's say you have sharded but not partitioned. What's that use case? When you are sharding, which means you have 2 database servers, but you are not partitioned, which means your data is not split, which means both the server has the same copy of data. This is classical case of read replica, where you have not partitioned the data, entire data is replicated there. There is no partitioning there. So this is a case of read replica. Right? This you would typically use to handle large number of reads. And then the final case when you have sharded the database and partitioned the database, which means that you have 2 database servers, each partition, and you have 2 partitions of the data, and each one resides on one server. This is to handle large reads and large writes both, because one partition was not able to, like, you have large amount of hits coming in for this partition and for this partition. To handle large writes, you partition the data and you kept it on two different servers so as to handle higher write throughput. Right? So all four cases of sharding and partitioning, this is how you can very easily visualize it. Right? Now on to the final part of it. Why are we taking this effort into doing this sharding and partitioning, and like what are the advantages of sharding or the advantages and disadvantages of sharding? So you would typically do sharding when you would want to handle large reads and writes. Now if you see here, with sharding you are adding one more database server into your scheme of things, which means that you can literally halve the load. By adding one more, you can halve the load on one database server and handle twice the traffic if you want to. Right? So you are just prepping yourself to handle large amount of reads and writes coming your way. Then to increase the overall storage capacity. Now, because you have multiple databases. Now, let's say, obviously, like everything has a limit, the disk of a database also has a limit. Let's say it is 100 terabyte. 100 terabyte is the limit. It's very high, but assume that 100 terabyte is the limit of one server. But you have 200 terabytes of data. Where would you store it? Because there is a physical limit of this database, you would have to have another database to increase the storage capacity so that you can store large amount of data. So that is another advantage of doing sharding. Then higher availability. That if one of the database goes down, other database can take it. Like for example, in case of read replica, if one of the database server goes down, you can very easily use this other database to continue serving the traffic. Right? Although sky is not always blue, what are the disadvantages of sharding? It's operationally extremely complex. When you have multiple databases to do, like in case of read replica, you have to ensure that the replication lag is bare minimum, data is continuously replicated and whatnot. When in case of sharding, when you have partitioned and sharded both cases, you need to deterministically know where the partition lies and you would go to that shard and get it. And in case of one of the database server getting hot or one partition getting hot, you would have to rebalance and move that partition into other database. So it becomes operationally very complex. But at scale, you would have to do that. Right? There is no way out for that. And the biggest disadvantage of sharding is that cross-shard queries are very expensive. Let's say you have partitioned the data, put it across two shards. And now what you would want to do is you would want to join the two tables. One is on this shard, one other one is on this shard. How you can do that? You cannot do that. Right? So cross-shard queries becomes extremely expensive. So it's first of all not really efficiently possible. It becomes expensive. Plus it becomes very easy to even communicate what's happening, impacts the throughput, increases the latency and whatnot. So typically whenever you are sharding, you would always think about a way where you are sharding such that all of your queries are answered only from one shard. You would never have to do cross-shard queries. But in case you have to do, brace yourself, it is going to be super expensive. Super expensive with respect to time, with respect to compute resource, with respect to everything. Right? Nice. Yeah, basically that's it. That's it for this video. I hope you now know the difference between sharding and partitioning, where to use, how databases evolved, and how in real world we approach situations like this. So these concepts are not just theoretical, given you practical usage, like practical use of all of these 4 use cases. Right? So yeah, that's it for this one. If you guys like this video, give this video a massive thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week. And I'll see you in the next one. Thanks a ton.